So when I say an improper integral, the most basic kind is this. You have an integral which is a definite integral, but you have a little infinity there, okay? And that is something that we're going to, when we see that, we're going to say this is called an improper integral. Now what could that possibly mean? Does it make any sense? Well, to make sense of this, what I'd like you to do is draw a graph that the fundamental theorem of calculus tells us we associate with this. So here's my x and y axis. What's the function we're dealing with? 1 over x squared. Do you guys know what the graph of that looks like? Well, yeah. It goes through the point 1, 1. But it is asymptotic at 0, and it's also asymptotic where? Well, at 0 this way, right? So this is the function. F of x is 1 over x squared. It goes through things like 2 comma what? Wait a minute. 1/4. Okay, so actually it kind of gets down there quicker than I was representing it, right? By the time you get out to 3, where are you? 1/9. Okay, so we get out there pretty, we're starting to hug that x-axis already. See that? By the time you get out to 10, you're at 1/10. No, 1/100th. Okay. So let's draw a picture of the area under the curve from where to where? From 1 to infinity. All right. So how much area is that? Are you sure? Because if it were, then why would we have a section on improper integrals? This brings me to my favorite picture in all of calculus, which I have to show you. And it's the sandwich picture. So my Calc 1 class has seen this. So this is my peanut butter and jelly sandwich my mom used to pack in my lunch. Now I have to make my own. I brought pizza today. But anyways, when Mom packed your sandwich, my question to you is, how did she cut it? Or did she? What's that? You got diagonal cuts? How many got diagonal cuts? See, my mom didn't do that. Yeah, maybe it's where I grew up. My mom would cut it this way. How many had moms that cut it that way? How many diagonal? Andre, what'd your mom do? All right. So anyways, when I was real little, my mom would cut the sandwich like this too. Did you guys, anyone have this happen? Because then I had quarters. Then I could pick it up. I still remember this. So anyways, here's what happened. I would eat maybe this much of the sandwich and then throw the rest away. So how much of the sandwich did I actually eat? 1/2. But then, if I'm really hungry, I would also eat this piece. So how much did I eat? 1/2 plus what? 1/4. Okay? Then, because I was such a math nerdy kind of kid, I would cut this in half and eat this much. So what did I do? I ate another 1/8. And then I cut this in half. And what did I eat? Plus 1/16. Now I'm going to do something that you guys all like to do, which is recognize patterns. So you know what I'm going to do next, right? How many know what I'm going to do next? So I'm just going to write dot, 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 since you all know what I'm doing. You guys follow that? So here's my question. If I write that, and if I write equals, can you tell me what that equals? Now wait a minute. How many different things are we adding together? An infinite number. But you guys just told me you can add an infinite number of things together and get it to equal 1. Is that what you're telling me? I'm adding an infinite number of things together and getting it to equal 1. That's chapter 9. What we have there is what's called an infinite series. Now, I'm not supposed to do that yet, but it's my favorite picture in calculus because to me, that's a fascinating fact, that somehow you can add an infinite number of things together and the result might be finite. And that's exactly what I'm doing here. When I say I'm going to integrate from 1 to infinity, you can't integrate from 1 to infinity. So what you do is we do the following. We write this definition down. This equals the limit as, I'm going to use the letter b because a lot of times we integrate from a to b. The limit as b goes to infinity of the integral from 1 to b, and instead of writing 1 over x squared, since I'm going to have to integrate, I'll write x to the negative 2. It makes it easier to integrate, dx. But this is, by definition, what we mean by infinity. On the picture, what it means is, look, somewhere here, this is the line x equals b. Could I compute the area under the curve from here to here? Yeah. But that would not be the full answer. So what I do then is I move b over some. Then I get closer to the answer, right? Kind of like in the picture, I eat more of this sandwich, I get closer to the actual answer, which is going to be 1. See, 1 here is a limit, right? In the limit, I would eat 1 sandwich. Okay. So now let's finish the problem. All we're going to do is do an integral, and at the end, I'll take a limit, and that's an improper integral. That's all you do. So, how do you integrate x to the negative second? Negative x to the negative 1, and we're going to evaluate this from where to where? 1 to b. Okay? And then I'll take the limit after that. Because infinity is not a number. It's saying we're making x grow without bound. So to be real precise, this is what I want to do. And so now I write limit as b goes to infinity of, all right, now I have to be real careful here. There's lots of negative signs, and they're confusing. So what do I write? Let's see. Negative. What's this negative 1 mean? Okay, so 1 over b minus negative, right? 1 over 1. Okay, so this is the limit as b goes to infinity of negative 1 over b plus 1. Now wait a minute. As b goes to infinity, you tell me what happens. What goes to 0? This piece goes to 0. And so what's the entire limit? 1. So that's the area under the curve. Isn't that cool? Good thing I showed you the sandwich picture, or you might not have believed it. But that is a finite answer. Okay, so I want you guys to try one now. Very similar, and then we'll say, yeah, we get this. You guys were trying this, so if you followed my advice, the first thing you did is you said this equals limit as b goes to infinity, integral 1 to b, x to the what? Negative 1/2 dx. So this is the limit as b goes to infinity of 2x to the 1/2, right? Okay. And we evaluate that from 1 to b, and then we'll take the limit. So this is the limit as b goes to infinity of 2 times the square root of b minus 2. So what's that? What's the limit as b goes to infinity of 2 times the square root of b? When b gets large, guess what? So does 2 square root of b, right? Like If you put in 1,000,000 for b, what's the square root of 1,000,000? 1,000. So this would be 2,000. Yeah, this limit grows without bound. So what's that mean? Yeah, it does not exist. Here's what it means for us. Let's draw a picture of the graph again. Now, what's the graph of this function? Well, it goes through the point 1, 1. What else does it go through? Well, it goes through 4, 1/2, right? So actually, isn't it asymptotic? Yes or no? Like, you put in a really big value for x, doesn't it go close to 0? Yeah. But for some reason, this is too much area. The area here grows without bound. Why? It sure looks similar, doesn't it? So we're touching upon what I think is a mystifying point at first, but will be a very important point about Chapter 9. That sometimes these limits exist and are finite, and sometimes they don't. And we're actually curious about, well, when does it happen and when doesn't? And it turns out that when this happens, okay, we will use the following language. We say this integral diverges. But that's kind of weird. This improper integral diverges. When do we usually use that word? When we're talking about what? We didn't study series yet, right? What did we study? Yeah, when we had asymptotes, that was converge, right? So it turns out that, see, this is a limit, right? If the limit exists, we say the improper integral converges. Since the limit doesn't exist, we say the improper integral diverges. Does that make sense to people? Yeah? Okay. Now, if we wanted to, we could follow Clayton's question and say, look, in general, if I have some power here, P, and I integrate 1 to infinity, when does it converge and when does it diverge? But I'm down to 9 minutes, so I'm going to put that question on hold for a little while. We may come back. Okay. Why are you guessing that? Okay, so you could say, hey, P was 2, is that what it was? ID 1 over x squared, and it converged. And P was 1/2 and it diverged. So maybe, yeah, okay.
Also because when you take the half ones, they're ones that are smaller than 1/2, it's going to bring a whole number out in front instead of...
Yeah. Although, let me ask you a question. What was the problem here? Was it the number in front or was it the function? It was kind of the function. But if we look back at the first example, what was the function? It was, yeah, this was negative 1 over x, right? So you guys are on to the right idea, and this might be worth doing, but not right now. I want to show you something else. I want to show you that you could do problems like this, too. And that's not going to blow us away, I don't think. I mean, here, let's draw a graph again. What does e to the 5x look like if you graph it? You guys know? Y equals e to the 5x. At 1, it's going to be e. What is e to the 5? How big is that? Pretty big? What if you put in x as 0? That's what I like to put in. All right, so exponential functions go through 0, 1. At 1, it's e to the 5, which is pretty big. By the way, notice where are we going to? We're going all the way to x equals 10, right? So what's the output? Where's e to the 50th? Way up there somewhere is e to the 50th. I don't know where. I don't know if it hits the moon or not, but we've heard of something called exponential growth, right? So it's something like that. I think you actually wouldn't see this. I think it would take off much sooner than that. But then what happens when you go to the left of this function? Do you know? It approaches 0. Okay. Sometimes that's called exponential decay. And it's asymptotic. And that's why this is going to make sense. So we're finding all the area to the left, all the way up to e to the 50th. Okay? Okay, so this is the limit as, I'm going to say, a approaches negative infinity. The integral from a to 10 of e to the 5x dx. So this is the limit as a approaches negative infinity. And how do we integrate this guy? I think I need a 1/5, but yeah. E to the 5x, right? And we go from a to 10. So this is 1/5 e to the 50th minus 1/5 e to the 5a. And I'm taking the limit as a approaches negative infinity of that. So this is going to equal 1/5 e to the 50th. Now what happens when a approaches negative infinity here? Where does this guy go? Right? Doesn't this go to 0? 1/5 times 0. So that's 0. So the answer is, that's how much area is under the curve. 1/5 e to the 50th. But it's finite, right? It's enormous, but it's finite. Sometimes that's all you care about is the integral finite? Okay. This is for what to do here? First we're going to do limit as b approaches infinity. And then I'm going to write integral from 1 to b. And what am I going to write? Okay, x to the negative p dx. So this is the limit as b approaches infinity. Now, do you guys know how to integrate that? P could be any number you want. Yeah, that's what I'm saying. Can we just do it in general? You can? What would it be? X to the negative p plus 1. Do you guys agree? Divided by what? Negative p plus 1. Evaluated from 1 to b. How many like that answer? Do you always get this? Are you sure? P is a number. See, there's this thing you got to watch. What if P equals 1? That's a separate case. Why? Because then you can't have 0 in the denominator, right? Yeah, we didn't do P equals 1 yet, but we could do it separately, right? If P equals 1, so a separate case, if P equals 1, we're integrating from 1 to b, and we're doing the limit as b goes to infinity, 1 over x dx, right? That's a special case I'll do on the side. Okay, but other than that, we've got it. We have a formula here. So this equals the limit as b goes to infinity. Now, let me think. Instead of writing b to the negative p plus 1, are you guys okay if I write b to the 1 minus p? Right? It's the same thing. Over 1 minus p minus, and then what happens here? You get 1 over 1 minus p, right? When you put in the 1. Is this okay? Okay. So the question is, what happens? Well, sometimes this equals infinity, and sometimes it's finite. So let's think about the examples we already had. When did we get infinite? That was when p equaled what? 1/2, right? And why did we get something infinite? Because we were taking b to the 1/2 power, that was the square root, and we said when b goes to infinity, that's going to grow. Now, the case where we got something finite was when p equaled what? 2. Why was it that we got a finite number? P was bigger than 1, which means this exponent is negative, which means where is the thing really at? Denominator. So this term went to 0 in that case, right? So you're going to get something finite if p is what? Greater than 1. And you're going to get something infinite if p is what? Less than 1. What about if p equals 1? Well, I'm actually out of time, so if you want to go, try it at home. Okay? If you want to stick around 1 minute, I guess I'll do it. All right. What do we get? Natural log of x plus, oh no, no plus c, from 1 to b. So this is the limit as b goes to infinity of the natural log of b minus, of course, what's the natural log of 1? That's 0, right? So it's just the limit as b goes to infinity of the natural log of b. Oh, do you guys know what that is? Well, we should look it up.